Elliot Roos.
Thank you. Thank you. Very nice to be here today. Thank you for having me. I'm very excited to talk about our project. So I'm going to talk about the development of open source bionic legs. Let me share my screen or start presenting. You guys see my screen and hear me okay? Okay, so maybe one thing I wanted to tell you about me before I get started is I was not a particularly good student in college, or really even in grad school. But in college, I worked in auto racing. That was kind of the thing that I did. I didn't spend much time at school. I just kind of did my classes and went back to work. And it wasn't really until I began to see that auto racing, which was insanely cool, wasn't fulfilling me, that I decided that what I really wanted was my work to impact people, and particularly people with disabilities. So then I left auto racing, went to grad school, and the rest is history. Now I run a research lab at the University of Michigan to talk about a project developing an open source robotic leg. And this is a presentation that I gave to the National Science Foundation. So the text might not be exactly like ideal for this audience, so I'm probably going to talk over top of it. First thing I want to do is give you a little bit of a sense for what we do in my research lab, the Neurobionics Lab. We study basic biomechanical science. And what I mean by that is we study how the mechanics of the legs are regulated by the nervous system during gait. And we use this as a set of instructions. And the set of instructions we use to build better wearable robotic technology. So we build robotic prosthetic legs, that's what we're talking about today. We also build exoskeletons, and some of my work also at Google X kind of is involved in the kind of wearable robotics side. What's unique is we kind of do these things together and they feed back on each other. So the science that we're doing drives wearable robots that we build, like exoskeleton and robotic prostheses. And we also use novel robotic systems to answer fundamental science questions. And that's something I won't really talk about kind of in this talk today. Okay, so let's think about like open source bionic legs. Why might we need this? And I would just say that control is one of the greatest challenges for robotic prostheses. It's one of the main reasons why you don't see robotic prosthetic legs in the public ever. If they make a mistake, someone can fall down a set of stairs. So that's a whole different set of risk than something like upper limb robotic prostheses, which if you make a mistake, it's not so dire. Fortunately, to study these control challenges, to build these instructions, we have researchers kind of around the world and around the country studying these strategies. But before a controls researcher can study how to control robotic prosthetic legs, they have to build a robotic leg first. And that takes hundreds of thousands of dollars and many years. So the goal kind of for this project is we wanted to build a system that's open source that would prevent people from having to kind of start over every time, which is bad because it hinders comparison. It's difficult to know whether the results from control strategies stem from the different hardware that people use, or whether it stems from the control strategies, and it's incredibly inefficient. We're spending this money and time over and over again, and we really should be using that money to address the challenges in mobility that these people have, not sort of reinvent the wheel. The leg that we built is something called this open source robotic leg. It's 2 degrees of freedom. So it's a knee or ankle that can be used together or separately. And something that's kind of neat is we leverage technology that was developed from the drone industry. So now we're looking like inside. So in order to build a robotic prosthetic leg, we have to choose a motor. So that's going to act like the muscles. We have to choose a transmission, and that changes kind of the amount of effort that it provides, how fast it can go, to be put in kind of a environment that's similar to the way humans move. So we use motors that were developed by the drone industry, that lowered the transmission ratio, and we used low cost, easy to obtain transmissions, which were belt drives. Let's see if I can move this forward just a bit. Another thing that we did that was intentional was provide lots of sensing options. So people who are developing control strategies need to be able to sense what's going on with the robotic leg to be able to understand what's happening and tell it what to do. So we made sure to add many different sensing options. So 6-axis load cell that tells how the foot is interacting with the ground. Then we also have sensing that tells us the joint angles, how much effort the motors are providing. So kind of similar to how much force your muscles will be providing. And all this information can be used to tell the system what to do. We also invented a new type of spring, which I want to talk about for just a second. Springs are kind of important in wearable robotic technologies. One reason springs are important is they store energy, just like the tendons in your body. So we store energy and then we can return it without having to use the battery to provide it. So it has other properties that are positive. So something called improved shock tolerance. So if you kind of bang your leg on the ground, it doesn't cause a ripple of force that can be catastrophic. So we designed a system that can be used by people who like springs and people who don't like springs. People who don't like springs typically don't use them because they add complexity and mass. The type of spring that we developed was this new type of torsional spring shown here. It's 24 discs, and what's kind of neat is we were able to include these springs in this design at no added mass or complexity. So what we did, now we're looking at a kind of cross section of the knee. So we've cut it in half and we're looking into it, and we can see we have these springs that we stack up inside the transmission, which costs no volume and very little mass. So that's kind of a neat addition that we had to this project that helped researchers build better control systems and make the legs respond more like the natural human body. When selecting and building a wearable robotic technology, one thing we have to do is make a selection of what motor to use. And like I mentioned before, we use motors that were developed by the drone industry. When selecting a motor, the thing that we care most about is how much heat it produces. Heat is really like the governing element that restricts performance. When the system gets too hot, we have to stop using it or modify control. So in order to design a system that uses the motor and prevent it from getting too hot, we need to know some properties about it. Most of the time, motor manufacturers tell us that information. Drone motors do not do that. They're built for drones, which have lots of air that blows over them. They're kind of in a different thermal regime than what we use. So we have to calculate these parameters ourselves. So the way we did that was we sent electrical current through the motor and watched it heat up. And you can kind of see here, as we do this, the motor's going to get hotter and hotter. And we're measuring like how heat can go through the motor and into the atmosphere. And that helps tell us like how much energy we can provide to the robotic leg when trying to make it walk or act like humans. So it's kind of neat. In addition to building the technology, specing a motor, we have to tell like how well it can control or perform. And one of the ways we do that is by a set of tests that we run. The tests that we run, I'm going to call like this closed loop control performance, which you maybe don't really need to know, but we can control different things. We can control how much effort it provides or torque. We can control its position, so where it goes in space, its joint angles. And we can control the kind of mechanics of the system, so what kind of system it acts like. And I will show a video of that or some things you might think are neat. So here we're quantifying the performance of the controller, so how well it can do what we tell it to do. And we're testing how fast it can go to a desired position. So we're going to tell it to go to these different steps, and then we're going to track how fast it can go. And this is kind of a standard way to kind of quantify control strategy and control performance. What I want to, okay, these plots are probably not helpful, but they're showing the same information in something called the frequency domain, which we'll see. A more intuitive test would be to say, okay, we want the control system to provide no effort. So what we want the system to do is to reject its internal friction and loss. And so if we can move it around with a cracker and the cracker doesn't break, then the control is doing a good job. So this is a way that we're quantifying the control. So we're looking at the knee here. That would be the top of the person's thigh that's moving around. And we're able to move the system without breaking the cracker, indicating the control is good. That's a bona fide robotics test right there. What I want to show now is a video. Hopefully this kind of comes through. Actually, let me optimize for video real fast. Okay, so let me play this video. This is what shows our open source. reason I wanted to show that video is because it kind of shows the intent of the project. We built this leg to get it out there in the research community, testing control strategies and eventually making a difference in people's lives. And that's very kind of showcasing the state of the art of this, not only robotic leg hardware, but also robotic leg control. He was able to walk around this hospital, do different activities, all kind of. I want to take a minute and tell you a little bit about some resources that exist. One is our website. So this is a website to learn all about this project, and actually it provides all the information needed to develop one of these systems. So like there's purchase parts, instructions on how to assemble, the bill of materials. These are solid model drawings for manufacturing. There's detailed assembly instructions, detailed control instructions. To check it out, it's opensourceleg.com. So we started this project 3 years ago to kind of get it into the research community to advance development. And I'm kind of excited to say we have about 10 institutions kind of using the leg right now, which is really wonderful. And in terms of kind of other media, popular culture, there's articles on this leg that were both produced by companies like Digital Trends or Fast Company or Freethink, and then trade magazines, which are important on our side to get information about this project out to engineers and researchers who can use this project to advance control strategies and help people with disabilities. We also presented at the Amazon conference where we demoed this robotic leg with Terry, was the individual you saw in that video. So not only do we talk about the design, which is more along the lines of what I talked about today, but we talk about the control, the artificial intelligence control strategy that tells it what to do. So that video is on YouTube. If you're interested, let me know. I can post a link. It has a not only neat description, but a very cool on-stage demonstration, which is almost unheard of in our field, to do an on-stage demonstration due to the risk. And then finally, kind of I wanted to mention, hopefully you guys got these resources, but we've created a brochure and kind of booklet for teachers and students. This is an example. I think I sent it out earlier. But it's information for students to help learn about not only the field, but how you can get involved, the things that maybe you want to focus on earlier in your education. There's a worksheet and a presentation for teachers. So please let me know if you're interested in this, if you haven't seen it, and share it if you have anybody you think would be interested. Thank you very much. This was great. I hope.
Thank you, Elliot. So students, I wanted you to meet a professor who's running a lab. A little bit later today, you'll hear from Atul, who's the department chair. Elliot's kind of just beginning. Some of you may end up going to University of Michigan and being part of his lab, and he's showing you the work he's doing. And you saw the actual presentation that he's using to pitch to get funding. So in a second, I'm going to introduce Linnell Williams. Is there a student that would like to ask Elliot a question? I know we're just getting into the rhythm here. So if someone does want to...
actually, John.
What's that?
Great questions. I'll just read them off. I don't know if you can see them there, Elliot, but how durable are the limbs? And how do people control the leg? And what is the cost of one of those legs?
Yeah, great questions. Durability is a huge concern. So if it's not durable, then people conducting experiments have to stop the experiments, fix the leg, and that kind of thing. So durability is a really big priority for. And one of the ways that we help make the leg durable is by making it very simple. So that leg, I would say, is it's very, very simple design in motor and transmission. So that's kind of one way that durability is an issue, and one kind of strategy we use to address that. Cost is about $35,000 for that leg. I'd say that's much less expensive than other legs, but still very expensive. We're working on a generation 2, which we hope would be about $15,000. So we have some prominent design changes that we would implement, which I think will help people get access to the leg.
Great, thanks, Ben. Yeah. And if anyone wants to connect with Elliot in the future and you're intimidated to talk to him about bionics, you could start by cars. Like I said, he worked on the Formula One team, and he said that his introduction to science was through cars.